Say I have an arylamine, we can do some reactions with it. We've seen quite a bit in the electrophilic aromatic substitution chapter, so we'll review some of that right now, but introduce a couple of useful, helpful reactions. First of all, as a reminder, the NH2 group is one of the most powerful activating groups in electrophilic aromatic substitution reactions. That's because nitrogen's lone pair donates in very effectively, charging up that benzene ring with extra electron density to go off and attack electrophiles. So if I have aniline, right, that NH2 on the benzene ring, I don't even need any catalyst or anything. I can just add bromine to it and it'll very quickly brominate in the ortho and para positions exclusively. It's impossible to monobrominate, right, or monohalogenate aniline. It's just such a strong activating group that before we know what happened, we just fill in bromines in all of them. But say I want mono substitution. Say I only wanted one bromine in the para position. What we do, or this is any electrophilic aromatic substitution reaction, right? We wanted an acylation or something like that. If I only want it just once in the para position, instead of using aniline as our reactant, if I use acetic anhydride, right, CH3, C double bond O, C double bond O, CH3, that turns the amine into an amide, because remember, nitrogen has the lone pair, that's the nucleophile. The leaving group is the O, C double bond O, and everything beyond it. That turns our NH2 into an NH, C double bond O, CH3. Now, this still has a lone pair on it, so it's still ortho-para-directing and it's still somewhat activating, but because this lone pair is shared between the benzene ring and the amide resonance, right, where I make an O minus up in here, that means we have less donation into the benzene ring here than we did with just aniline. So that means I can do a Friedel-Crafts acylation reaction like this. We could do any electrophilic aromatic substitution reaction, and we'd be able to get just a mono substituted product. That would be great if we wanted the amide, but in case we still wanted that amine, we can just use hydroxide and hydrolyze that amide. OH minus is the nucleophile. Ends up the whole rest of this molecule here is the leaving group starting with the nitrogen on. So we get acetic acid, right, off here, C double bond O, CH3. Right. But then we get our amine back. So acylating a amine like aniline will help control its reactivity. Right? It doesn't make it so donating, so hot for electrophilic aromatic substitution reactions that we can actually just control the reaction much better. One new reaction we'll talk about here in this chapter, other than our Hoffman elimination, the other new reaction, I guess, is a Sandmeyer reaction. And I think you'll like this reaction. It's sort of an all-purpose electrophilic aromatic substitution reaction. We can make so many different functional groups based just on this one reaction. So to start, we have to start with aniline. Okay? We have to start with an NH2 group on a benzene ring. If I react that with nitrous acid, which is HNO2, right? It's not nitric, it's not the strong acid, nitric acid, which is HNO3. This is nitrous acid. What we get is a diazonium salt. So that's where we have benzene, and then N triple bond N. And that first N has 4 bonds, so it's positive. That's our diazonium salt. And diazonium salts are very useful because if we react that diazonium salt with a ionic copper compound, okay, the minus part, the anion of that copper compound will totally replace the diazonium salt. It's not a mechanism that we need to worry about. It involves radicals and other bizarre things, but it's really easy to follow, right? We start with aniline, HNO2, get the diazonium salt, then copper and Cu plus and whatever minus it is we want to replace it with. So if I want to replace an NH2 with a bromine, I do HNO2 to make the diazonium salt, then I do copper bromide, CuBr, and that puts a bromine in its place. Okay. That's it. These other reagents here are present in small amounts. I really wouldn't worry about them too much. The stoichiometric one is the nitrous acid. That gets the diazonium salt. Then we'd use copper bromide, CuBr, to replace it with the bromine. Turns out iodine is reactive enough. We don't need copper iodide. We just use I-. That'll replace a diazonium salt. But all the other ones, here's orthomethyl aniline. We make a diazonium salt out of it. We do copper cyanide. We end up with a nitrile in its place. We end up with C triple bond N. And look at this nitrile, right? C completely bonded to an electronegative element. It's the same oxidation state as a carboxylic acid. So reacting aqueous acid with a nitrile converts it into a carboxylic acid. So that's a way under essentially neutral conditions to get a carboxylic acid on a ring, right? The other way, of course, is the Grignard reaction, but if we have anything acidic in our molecule, that'll interfere with the Grignard reaction. So we could make a phenyl Grignard, right? Phenyl magnesium bromide, react it with CO2 to get a carboxylic acid, but Grignard reactions are a little more difficult than this. This is done under pretty normal conditions. Finally, if I have an NH2, I can make a diazonium salt. I react it with copper oxide, Cu2O. I get an OH group. Okay? This is the first way so far that we've seen to actually introduce a hydroxyl group on a benzene ring, right? Really the only useful way that we know of anyway in this class to make a phenol. Okay, so if your product is a phenol, if it's a benzene with an OH on it, and there was not a phenol in your starting material, then this is the reaction. Okay, so pay extra close attention to this one. NH2, right? So an aniline plus HNO2 makes the diazonium salt. Then copper 1 oxide, Cu2O, right? Cu2O makes the hydroxide. Another thing we can do with the Sandmeyer reaction is make an NH2 into a temporary directing group. So, for instance, imagine we have paramethyl aniline, right? Got CH3 across from the NH2. If I just react that with bromine, I quickly brominate both ortho positions, make a diazonium salt out of the NH2. Then I react that diazonium salt with this very interesting compound, H3PO2, hypophosphorus acid. P double bond O OH, and then two H's on that P. Those two pHs. It's a very powerful reducing agent. It replaces a lot of things with hydrogens. So this is its most famous use in organic chemistry, and the only thing really, I guess, that organic chemists really use it for mostly. So what it does is replaces a diazonium salt with H on an aromatic ring. So that allowed us to introduce this amine here to direct bromines, right, very effectively, and then we took it out. The problem with just having toluene with bromination is that methyl is a weak ortho-para director. We get some ortho, we get some para to the methyl group, right? If we wanted 2 meta to the methyl group, what we do is we do the NH2 as a temporary directing group and then remove it with this H3PO2. Another example, if I want to make 1,3,5-tribromobenzene, not immediately clear how we would just form that from just plain old benzene, but I know that if I had aniline, right, just plain old aniline tribrominates
in ortho and para positions like that. So if I was able to remove that, like we saw before, that'd be pretty easy. So aniline, or that tribromal compound, could just come from aniline, NH2. We can't introduce aniline directly onto a benzene ring, so that has to come from nitrobenzene. And we saw in the electrophilic aromatic substitution chapter how to get a nitro group onto benzene, right? HNO2, H2SO4, or HNO3 nitric acid. That means that we have the power now to either make a nitro or an NH2 group, right? The nitro has to be converted into NH2 like we saw with H2 in catalyst. But either of those can become all of these. NH2 doesn't get oxidized into nitro very well. We can sort of take that out. But if I have any, I guess I don't really need those first two we said, but we can take benzene, make that into nitrobenzene, can make that into aniline, and then through the Sandmeyer reaction, like we said before, we can make that into we can make that NH2 into a bromine, into an iodine, into a cyanide for a nitrile. I showed you on the last page how that nitrile can be made into a carboxylic acid. We can use Ag2O to make that into a hydroxide. Or, using what we saw before with that H3PO2, we can just get rid of that group altogether.